I'm Tammy Kolda, an applied mathematician, and this is Unlocking LaTeX Graphics. On this channel, I present tutorials on using TXE and PGFPLOTS. The videos on this channel are based on my book, Unlocking LaTeX Graphics, as well as some bonus materials. Today is the final part of my four-part series on drawing slope fields in LaTeX, which was prompted by a watcher question. Today's version is using PGFPLOTS and PGFPLOTSTABLE entirely in LaTeX without any external scripts. As a quick refresher, a slope field is a way to visualize a differential equation of the form dy dx equals f of x, y. At each point on a grid, you draw a short line segment whose slope matches f of x, y. In episode 60, I showed how to draw slope fields using plain TXE with nested for each loops. That worked for simple equations, but failed for functions like the exponential that produce large values. It also required you to draw your own axes. In episode 61, I introduced PGFPLOTS tables. I showed how to read, display, and create tabular data. This is the foundation of today's approach. In episode 62, I showed how to use PGFPLOTS quiver plots with external data files generated by a Python script. That approach is the most robust because Python can handle many more functions without numerical limitations. This is actually my recommended approach. So if you want the most robust way to draw slope fields, go back and watch that episode. Nevertheless, today I'll show you how to combine PGFPLOTS tables and quiver plots to do everything inside a single LaTeX document. So let's get started. Let's set up our document. I use the geometry package to set 1-inch margins. I use the parskip package to add space between paragraphs. I use the hyperref package to link the author name back to the YouTube channel. The key packages here are PGFPLOTS and PGFPLOTSTABLE. We covered PGFPLOTSTABLE for the first time ever in episode 61. In the PGFPLOTS set block, I set the compatibility to version 1.18. I set scale on the axis, which I generally recommend. I set axis lines to middle so the axes cross at the origin. I use axis equal image to keep the x and y scales the same, which is important for slope fields so the angles look correct. I set enlarge limits to add a little bit of extra padding, and then I make every plot blue and ultra thick by default. To draw a slope field entirely in LaTeX, we need to create a grid of xy points using PGFPLOTSTABLE. In episode 62, we used Python script to generate this grid, but now we're going to do it with the create on use feature of PGFPLOTSTABLE that we learned about in episode 61. So I start, first of all, by defining 6 parameters that we're going to use to control our grid. I have xmin and ymin. They're each set to -2. I have xsamp and ysamp for the number of sample points in each direction. These are set to 5. And then I have xstep and ystep for the spacing between points, and I'm taking unit steps. Then I compute the total number of rows as xsamp times ysamp, and for a 5x5 grid, that's 25. And I have to cast that to an int. Now I define the custom style called xy grid using PGFPLOTSTABLE set. So this is a style that I am naming. It takes 6 arguments corresponding to our 6 parameters. So another episode, which I'll link in the show notes, I talked about styles that take arguments. This creates 2 columns, x and y, using these create on use expressions. The idea is that each row in our table corresponds to 1 grid point. I use floor and mod to convert the row number, represented here by PGFPLOTSTABLE row, to an appropriate x and y value. The floor of the row number divided by the number of y samples gives me the x index, and the mod gives me the y index. Now I'm going to use PGFPLOTSTABLE new to actually create the table. So far I've just set up this macro that I can call. And so now I'm creating the table. I pass in the xy grid style with our 6 parameters. I specify that I want columns x and y, and this is what actually triggers these create on use things to be called. Then I'm saying that I want n rows, in this case 25, and that I should put the result into the macro called myTable. Then I display the table with PGFPLOTSTABLE typeset, and we see the result here. Now, if you take a moment, maybe pause and stare at the table, you'll see that there is a problem. The point 0 minus 2 actually appears twice, and 1 minus 2 is missing. This is a floating point rounding issue inside the floor function that I'm using here. The PGF math library is computing the division slightly incorrectly, which causes the floor function to round down when it shouldn't. This is a problem with PGF math. It's not very accurate. The fix here is to add a small value inside the floor function. So I'll do 0.001 to nudge the result past the rounding boundary. This fixes it, and now we see that the point 0 minus 2 appears once and 1 minus 2 appears once. The grid is correct. This fix is not robust. For example, at first I was using 0.0001, but this didn't work for some of the other examples in this episode. But 0.001 seems to work, at least for all the examples in the episode. Now that we have our grid, let's compute the slope field. We need 3 more columns, f for the function value and u and v for the direction vector components that the quiver plot will use. If you remember from our prior episodes, what we want is a direction vector that has the slope of f of xy. So the u component is 1 over the square root of 1 plus f squared, and v is f over the square root of 1 plus f squared, or just f times u. I will add 3 more create on use columns here. The f column calls a function f of xy that we'll declare in a moment. The u column computes the horizontal component of the unit vector, and the v column computes the vertical component, and it's just f times u. Note that the f column uses this row x and this row y to access the x and y values from the same row. And u and v use this row f to access the function value from the same row. So be sure to create the columns in the order that they're going to be used. Let's replace all of this. I'm defining a formula macro for the plot title, and I'm replacing the PGFPLOTSTABLE new command. The key element here is this PGF declare function. And this is where you'll write down what your f of xy function is. Here I'm using x minus y. This is the differential equation we're visualizing. I still use the xy grid, and then I'm doing more columns now, x, y, f, u, and v. When I compile that, we see now that our table has 5 columns. Now let's turn this table into a slope field plot. I'm going to get rid of this table display, and I'm just going to do a Tixie picture. This is the same quiver plot technique from episode 62. I draw 2 sets of arrows, one with u and v, and then another with minus u and minus v. This creates a line segment centered at the grid point. We covered in the previous episode things like quiver scale arrows as well as the quiver plot. So now I have the basics of doing slope fields entirely inside LaTeX using PGFPLOTS and PGFPLOTSTABLE. Let's try a more complex equation on a larger grid. So I'm going to go back up here and I'm going to replace these parameters. I'm going from minus 6 to 6. 25 steps in each direction. I'm taking steps of 0.5. That's a 625 row table. Now I'll go back down to the place where I defined my formula, and I'll do something different. I'm going to use the formula dy dx equals sine of x plus y. Remember, PGF math trig functions expect degrees, so I wrap x inside the degree function. I'll compile that and let's see what we get. So that's very small and crowded. Now I've recompiled and I changed the quiver scale from 0.4 to 0.15, and I changed the size of the picture from the default to 15 centimeters by 15 centimeters. With 625 points, I need the plot much bigger, and I need to scale the arrows down so that they don't overlap. Now let's just show you how easy it is to change this. I'm just going to change the function here and the PGFPLOTDeclare function. So that's all I've changed here, and I'm going to make it sine of x times y. I compile that, and now we get that fun needlepoint looking pattern that we had in the prior episode. That's kind of nice. Now let's try dy dx equals the exponential of x minus y. Remember, this is the equation that we had trouble with in episode 60. because when we used TXE, the exponential overflowed. I'm not sure exactly why PGFPLOTS does a better job than TXE, but somehow when you're creating that table, the math is a little bit smarter. And we see here we get our nice looking plot and all the lines are there. Our last example is dy dx equals 2 cosine of x divided by y. This one is interesting because at some points the function f is undefined when y is equal to 0. In episode 60, we had some special case where we checked the value of y. That was kind of a hack and only worked for that function. In episode 62, when we were using the Python code, we checked to see if the function value was infinite. Technically, we checked to see if it was a number or not. And we substituted vertical line segments if it was not a number. Observe that when we plot this, we have no line segments whatsoever along the y equals 0. That's because they aren't defined. There's some infinity in there or something. The trick is to modify the u and v column definitions to detect when f is extremely large and substitute a vertical line segment instead. So we go up back here to where we do the create on use, and we're going to change that. It's going to be almost the same, but we're going to do an if then else statement. Basically, if the absolute value of the f is very large, so infinity or minus infinity, then we'll take the first argument, and otherwise we'll take the second. That's the same as we had before. So if the function value is infinite, then we're going to use 0, 1 as our u and v values. That will give us a vertical line. So let's see what happens when we recompile this. And there it is. You can see the vertical dashes along the x-axis where y equals 0. The slopes are infinite there, and we've correctly represented them as vertical segments. I hope you enjoyed today's episode on drawing slope fields entirely in LaTeX using PGFPLOTS tables and quiver plots. We covered how to create a grid of points with PGFPLOTSTABLE, including the floor function hack to make everything work. We computed slope field data, the function values, and the unit direction vectors as table columns. And we used the quiver plot technique from episode 62 to draw the slope fields. We successfully plotted several equations, including the exponential of x minus y, which didn't work that well in basic TXE. And we also handled the singularity in 2 cosine of x over y by detecting large function values and substituting inappropriate values to get vertical segments. If you run into any problems, the most robust approach is to generate your slope field data externally using a script in Python or whatever your favorite language is. That's what I had showed in episode 62. You avoid all the floating point quirks and limitations of PGF math, and it's much easier to debug. I include a link to the overleaf document I created today in the show notes. If you found this helpful or interesting, please click like or subscribe. If you have TXE or PGFPLOTS questions, please post them in the comments. If you want to learn more, please check out the other videos. I also have a book, Unlocking LaTeX Graphics, available for purchase at major book retailers. Thanks for watching.